Hi, so I'm Nadège, and I will now talk to you about the indirect search for dark matter in the Galactic Centre with IceCube. So we expect galaxies to be surrounded by dark matter halos with an increased density towards the center. And this higher concentration of dark matter at the center of galaxies would favor their annihilation into standard model particles. Making, for example, the Galactic Centre a good target for indirect searches. For this analysis, we will more precisely be looking for neutrinos originating from dark matter annihilation in the Galactic Centre. So in order to observe these neutrinos, we need a detector, and in our case, this would be IceCube, which is a cubic kilometer neutrino telescope located at the South Pole. And it is made of over 5,000 photosensors, which are located on 86 strings, which are buried in the Antarctic ice. And a denser subdetector is located at the center of IceCube and is known as deep core. So neutrinos are only observed indirectly as they are deduced from their interaction in or around the detector. This will produce charged particles, which would emit chunk of light as they travel through the ice. And this chunk of photons can then be detected by IceCube photosensors, and we can reconstruct some of the properties of the incident neutrinos, such as the direction, the energy, or the neutrino flavor. So the background of IceCube is dominated by atmospheric muons and neutrinos. But as you can see here, for upcoming events, the Earth acts as a shield against atmospheric muons, and we can get rid of this really important contribution from atmospheric muons. Unfortunately for us, the Galactic Centre is located in the southern hemisphere at declination of around minus 29 degrees. So neutrinos coming from the Galactic Centre are seen as downgoing events in our detector, which means that we need to consider a veto to reduce the atmospheric muon background. And this is done by only considering the deep core subdetector as our effective volume, while the surrounding strings are used as a veto. So you've seen this equation already. So we can estimate the neutrino flux from dark matter annihilation in the Galactic Centre from the following equation, where the dark matter mass and the neutrino spectra are given from theory. We have this term, which is known as the J factor and is driven from astrophysical observation. Lastly, there is the dark matter self-annihilation cross-section, on which we can set limits if no signal neutrinos are to be found. So for this analysis, we consider spectra computed with Charon. This package is based on PITIA and includes a new calculation of the electrolytic correction with processes which are not taken into account in PITIA. And you can get more information about the Charon package by looking at this poster. So the two plots on the right are showing the spectra for all the dark matter annihilation channel considered and for dark matter masses of 100 GeV and 1 TeV. So both spectra are at Earth for muon neutrinos. So the dataset considered for this analysis is called OSNext and is a low energy dataset which was developed for IceCube oscillation analysis. This dataset consists of 8.5 years of IceCube data taken from 2011 to 2019. And when compared to the dataset from the previously published Galactic Centre Dark Matter Search, which was only using 3 years of IceCube data, we can see that we get a better effective area by considering the OSNext sample with around an order of magnitude improvement. So in order to search for an excess of neutrino coming from the Galactic Centre, we use a bent likelihood method, which compares the data PDF to what we expect from the signal and background PDFs. The likelihood is computed by comparing the number of events bin per bin to the number of expected events. And this number of expected events is given by the total number of events in the histogram and the fraction of events within a specific bins. And this fraction of events depends on the signal PDF and the background PDF. So now let's take a look at the PDF we are feeding into this likelihood method. So for the background, the PDF are computed from simulation. This simulation are weighted with an atmospheric flux. And for our analysis, we consider three-dimensional PDFs with which contains the information about, so the angular information under the form of the opening angle to the galactic center, and the energy information and the flavor information. So here I represented the PDF, so the 3D PDF under the form of two histograms. The first one is a two-dimensional histogram with so psi, the opening angle to the galactic center, and the energy. And then the second is 1D histogram with the track probability. So the track probability of 1 means that the event will be track-like, while here the events are most probably cascades. So the signal PDFs are also computed from a simulation, but this time they are weighted with the annihilation spectra and the J factor. So for the spectra, we are considering the current spectra I introduced earlier for masses ranging from 5 GeV to 1 TeV. The J factor are computed with clumpy, and both the Navarro-Frank-White and the Burkett halo profiles are considered. So the PDFs shown here are the PDFs for the new channel on the left for a mass of 100 GeV, and here Toto channel for a similar mass. And they are both, both set of PDFs are assuming the Navarro-Frank-White halo profile. So this brings me already to the sensitivities we got for analysis. So here are shown the sensitivities obtained for all dark matter annihilation channels considered, for both the Navarro-Frank-White halo profile on the left and the Burkett halo profile on the right. And these sensitivities can be compared to the previous IceCube results in order to get a better idea on how things improved. So you can see such comparison on this plot, where our sensitivity is compared to the sensitivities of the two previous results. So namely the IC86 3 years galactic search for WIMP, and recently published dark matter search combining data from Antares and IceCube. So you can see that the sensitivity of this analysis show considerable improvement, especially at low energy, where we even probe lower dark matter masses than in the previous results. So this enhancement is mostly due to the improved data set that we considered. We also are considering more years of data. It is also due to the fact that now in the PDF, we are considering the energy information and the neutrino flavor, while the previous two results are only using the angular information. Lastly, we also switched the spectra used. So now we are using the current spectra, and the combined limit, for example, was obtained with the PPC4 tables. So in conclusion, the sensitivities obtained for this analysis are showing considerable improvement to the previous IceCube results. These better sensitivities are due to the combination of factors, which are the improved event selection, which also more years of data were processed. The fact that we consider the energy and the flavor information along with the angular information, and to a lesser extent, the change of spectra from the PPC4 tables to the Karen spectra. So this brings me already to the end of my presentation. Thank you for your attention.